Hi, welcome back to the lecture series on abstract major theory. Today in this lecture we will discuss Fubbini's theorem. Okay, Fubbini's theorem. Fubbini's theorem. So let us first state this theorem. Let f be a function from the product space x cross y to R. It's a real valued function. Be mu cross nu integrable. Where it's given that x as mu and y as nu, they are major spaces. Okay, so this function is mu cross nu integrable function. It's mu cross nu integrable function. Then we see that both the iterator integrals exist, and they not only exist, but they are also equal. Then both iterated integrals exist, and they are equal to the integral of f over the product space. Integral of f over the product space is equal to both the iterator integrals. It is called integral of f. Sorry, it's double integral here. It is the iterator integral, double integral of f, first with respect to the measure mu, then with respect to the measure nu, and it is same as the double integral of f, first with respect to the measure nu, then with respect to the measure mu. That is the statement of the Fubbini's theorem. If f is mu cross nu integrable function, then its both iterator integrals exist, and they are also equal. They are equal, and they are equal to the integral of the function f over the product space. Okay, proof of the theorem. Without loss of generality, we may assume that this function is non-negative. We may assume that the function f it's not equal to 0. It's greater or equal to 0 for all x belongs to x, y belongs to y. Otherwise we take it as positive and negative part, because positive and negative part, they are both non-negative functions. Okay, and we know that every non-negative integral function is an upper function. Then this f is an upper function, so we can choose upper function. We can choose its generating sequence, so we can choose the sequence phi and step functions. So choose a sequence phi n, and runs from 1 to over the product space, because f is integrable over the product space. Choose the sequence phi n of step functions, phi n of step functions, such that this sequence is non-negative, and it also increases to that the limit of this sequence is f of x y, and the sequence is monotonic increasing. Okay, it increases to this. This is true for all x belongs to x, y belongs to y. That's actually by definition of an upper function. Since this function is an upper function, f is an upper function, so we can find its generating sequence, and that you can see in the first course of the major theory, the lecture series on the first course of major theory, which I have already uploaded on my YouTube channel. You can see that. Okay, so this sequence always exist. And we know that this function, step function, it's an integrable function over the product space, and both the iterated integrals of this step function, they are equal. That we have already discussed it in the previous lecture. So we can write here this integral over x space, then integral over y space of step function phi and xy. It's d nu, that it's d mu here. Okay, this integral, it's same as, actually it's same as integral over y, then integral over x phi and xy d mu d nu, both are same. And I will use only this part here, this integral, first one. This integral is equal to, okay, this integral is equal to the integral of phi over the product space, it's integral phi n over the product space mu cross nu, and that integral increases to the integral of f. That's definition of an upper function, actually. That's the definition of generating secant. Since phi n is a generating secant, so phi n increases to f, and the integral of phi n is equal to, integral of f is actually equal to the limit of the integral of phi. That's the definition of an integral of, integral of an upper function, actually. F is an upper function, its integral is equal to the limit of the integral of phi n, where phi n is the generating secant of f. Okay, I name it star here. This expression is very important. Now now we can apply the previous theorem here. Now we have this gnx. Let's define this gnx, this new secant gnx, which is equal to the integral of phi n x, that's already defined, phi n x with respect to the major nu, because it's a function of y now for each fixed x. This is equal to the integral over y space of the function phi n xy, because phi n of x means it's equal to phi n of xy, where y is where we vary the y, keeping this x fixed, actually d nu. Okay, this is equal to this phi n xy, it's a step function, so it's equal to the integral, let me see the previous page again. What's phi n xy? It's a step function, so it has a standard representation, so I can write it as summation I runs from 1 to n ai, they are non-negative real numbers here, and into the major because we are integrating it with respect to the space x. We are keeping this keeping this x fixed, so we can write it as okay, it's a step function, phi n of xy, it's a step function, so it's summation of this, that it's the characteristic function of a I d mu. Okay, and this is equal to summation I runs from 1 to n, summation I runs from 1 to n, integral of this characteristic function, it's actually the major. So this is actually here you can write it as xy, and this is same as the summation ai integral chi ai x. You can take x also, it is d nu here, it's not d mu, it's d nu here. Okay, it's d nu, and this is equal to summation I runs from 1 to n ai, and this is actually the major nu star of aix. Okay, and we know that this nu star of aix, it defines an integral function by previous theorem, and we know that the finite sum of integrable function is again integral function, which is an integrable function, as also we know that this measure of this set is finite, because this phi n is a step function, so these sets ai, they are a finite measure over the product space, so it's a finite measure, And then by previous theorem, nu star of E of the function which maps x onto nu star of aix defined as an integral function. So that's an integral function, which is an integral function, which is an integrable function, which is an integrable function. It's by previous theorem that we have done in previous lecture, by previous theorem, or you can say by previous lecture. Okay, so this Gn, it's a sequence of so thus Gn is a sequence of integrable functions, over x. Thus Gn is a sequence of monotonic increasing sequence of integrable functions, and they are also monotonic increasing because phi is monotonic increasing. That's simple. And this Gn is Gn of x, it's monotonic increasing. And also we can see that the limit of integral of Gn is finite. Also limit of integral of Gn, which is equal to the limit of the integral, it's the double it's over x actually. So this is over x, integral of over x, integral over y, integral over x, integral over y, phi and x y. Then we have t nu, and this is by star, it's equal to integral of f d mu cross nu by star, and that's finite, because f is integrable by star. So this Gn, it's actually a sequence, monotonic increasing sequence of integral function, and it satisfies one more property, that the limit of integral over the space x is finite. So that means it satisfies the hypothesis of Levy's theorem. क्योंकि लेवी थ्योरम का स्टेटमेंट क्या है, अगर आपको याद होगा, Levy's theorem states that given a sequence of integrable functions which is monotonic increasing, such that the limit of the integral of that sequence is Gn is finite, then we can define the limit of Gn, which is an integral function. Then there exists a function g, and such that then there exists a function g which is integrable almost everywhere, and which is integrable, and Gn increases to g almost everywhere. तो ये आपने सारा लेवीज थ्योरम में किया है. तो लेवीज थ्योरम में आपने ये किया कि अगर आपके पास कोई भी मोनोटॉनिक इंक्रीजिंग सीक्वेंस होगी जो कि इंटीग्रेबल सीक्वेंस होगी, और जिसकी प्रॉपर्टी ये होगी जब हम उस पर इंटीग्रल लेंगे और फिर लिमिट लेंगे उस इंटीग्रल का, अगर वो फाइनाइट होगा तब हम इस जीएन सीक्वेंस का लिमिट डिफाइन कर सकते हैं, और वो जो लिमिट होगा वो भी इंटीग्रेबल होगा. ये आपने लेवीज थ्योरम में किया है. सो वी कैन अप्लाई हियर लेवीज थ्योरम by Levy's theorem. By Levy's theorem, there exists a mu integral function because it's over x space. There exists a mu integrable function g from x to r, such that this g and x, it increases to g of x. It increases to g of x almost everywhere. So I can find a set A of measure 0 such that g and x increase to g for each x in the complement, because it is almost everywhere property. So thus that's there exists, that's there exists a null set, a mu null set, okay, because it's over null, it's over the space x. Mu null set A such that this g and x, it increases to g of x for all x not in A, for all x not in A, for all x in the complement. Means this इसका मतलब है कि ये जो कन्वर्जेंस है ये ट्रू है उन पॉइंट्स के लिए जो x में नहीं है, और जो x में है उन पॉइंट्स के लिए ये ट्रू नहीं है, मगर x का मेजर क्या है 0. So that means this convergence holds almost everywhere. Okay, and this is finite also. Okay, this is finite. This g of x, it's finite for all x not in E. Now again, so we have this gnx, it increases to gx. So again, this since again we have this phi n of x y, it increases to fxy. That's in the beginning of the theorem. Now let's take its x section of this function of x. Okay, it will increase to fxyx. Okay, or you can simply write it as phi n, its x section, it's a function of y. Okay, it will increase to fx, and this is true for each x, for all x in x. Okay, so this is true for all x in x. So it follows that this fx is defined as a new integrable function, because phi n of x, it increases to fx, and limit of the integral of phi n of x is finite. So that means fx is new integrable function. So this means fx is new integrable function, because limit of the integral of phi n x, because limit of the integral of phi n x is finite. Okay, with respect to the measure nu. So that means fx is new integrable function for all x not in E, because this convergence, this limit exists, this one. Okay, because this limit exists for all x not in E. So here you can see this this gnx, it's actually the integral actually. Yeah, so gnx is what's actually gnx. You can see it at the previous page. What's gnx? So gnx is here. Let me see this gnx first. So what's gnx actually? So that's gnx, it's integral of phi n x. Okay, gnx is integral of phi n x, that I have to write here, gnx. So this is actually integral of phi n x, okay, with measure nu. Okay, this is gnx, right? This is your gnx, and it increases to gx, which is finite. So in limit of the integral of phi n x is finite, but limit of phi n x is fx. So that means by Levy's theorem again, fx is new integrable. Fx is new integrable. Okay, that's by Levy's theorem again. Fx is new integrable function for all x not in A. For all x not in E, and this g of x, which is by definition equal to the integral of phi n x d nu, and that's equal to integral, its integral over y space, phi n of x y d nu, and that limit, since phi n x increases to fx and fx is an integral function, by Levy's theorem this is equal to the integral y fx d nu. Okay, so that's your gnx. So that's the limit of gnx. This is true for all x not in E. Okay, because phi of x, it increases to fx, and by Levy's theorem we can pass the limit. Okay, this limit, integral of the limit is equal to limit of the integral. That's it. So for all x not in A, this is true for all x not in A. Now we use the star. Now what's star actually? And we can apply the theorem 21.6, which is actually that theorem is for actually upper functions, and here these phi n is integral of phi n is, they are all they are the integral functions with respect to nu measure. Okay, integral of phi n d nu, they are new integral functions. Okay, and they are also non-negative, therefore they are upper functions, and integral of this phi and d nu, it is increasing to fx. So by that theorem, the integral fx y d nu defined as an integral function, mu integral function. Okay, so let me write here what's actually star. So equation, from this equation star, we have integral over x, integral over y, phi n of xy d nu, then d mu. This is this increases to this is so this sorry, this one, okay, let me erase this. So this integral phi n of xy d nu, this is a function of x, and this integral of phi n of x nu, they are all non-negative functions, therefore they are actually upper functions, because every non-negative integrable function is an upper function, and also its limit is equal to, limit of integral of phi n is equal to integral of, also this limit integral of phi n xy d nu, it's equal to integral over y, it's over y actually, I can say it's fx d nu. So they are upper functions. This is the sequence of upper functions because they are integrable and non-negative. So sequence of upper functions such that the limit of that sequence is this one. Then by theorem 21.6, you can see that theorem on Albrecht's. By theorem 21.6, this integral over y fx d nu, it defines a new integrable function, the limit function actually. It defines a new integrable function. It defines a new integrable function. Okay, this function, it's a new integral function. And not only this, this is your gn actually. You can it's gn, your gn of it's gn of x actually. So this gn of x, it increases to this function integral y fx. So gnx is a sequence of upper functions, increases to integral y fx d nu. So then that limit is integrable function, mu integral function, and also the limit of the integral is equal to the integral of limit, and this limit integral of limit of gn is equal to limit of integral of gn. That's by theorem 21.6 on Albrecht's. You can see that theorem. But what's this limit of gn actually? So this is you are integrating over x space actually. This is x space. We are integrating over x space. This is over x space, and that's equal to integral over x space limit of gn. What's limit of gn? What's limit of gn? It's equal to integral y fx. This is d mu here, okay? This is d mu, and this is d nu, and here it is d mu, because this limit of gn is equal to integral over y fx d nu. Okay, then we have d nu. It's equal to limit over x. What's gn of x? What's gn of x? It's integral over y of the function phi n of x comma y d nu, then d mu, and that's equal to the limit of integral of phi n d mu cross nu, because we know that the step functions their iterated integrals are equal, and they are equal to the integral of the function over the product space. Okay, and this limit is equal to integral of f d mu cross nu. So that means this integral of f d mu cross nu, on this side we can write here, on this side we can write here, this implies integral over x, integral over y, f of x comma y d nu, then d mu, it's equal to integral over f d mu cross nu. And similarly we can see integral over y, integral over x, f of x y d mu is equal to integral f d mu cross nu, and this one can be obtained by using this equation, because I have already mentioned this one. We replace we have used this equation, this is equal to this, तो हमने इस इक्वेशन का एक्चुअली यूज़ किया. अब हम इसके बाद क्या करें, हम इस इक्वेशन का यूज़ करेंगे, तो यहाँ से हमें जो इसका सेकंड इंटीग्रल है वो आ जाएगा. तो जब हम दूसरी इक्वेशन का यूज़ करेंगे तो वहाँ से ये आपके पास आ जाएगा. सो देयरफॉर बोथ द इटरेटिव इंटीग्रल्स आर इक्वल एंड दे आर इक्वल टू द इंटीग्रल ऑफ एफ ओवर द प्रोडक्ट स्पेस. Thus integral of f over the product space is equal to the iterative integral over x, iterative integral over y, f d nu dy d nu. Okay, this is same as integral over y, integral over x, f d mu, then d nu. This proves the theorem, Fubbini's theorem. Now we will give an example of a function in which both the iterative integrals exist, but the function is not integrable over the product space. So that's this example. So let's take, actually I have already discussed this, but here I will prove this. Here I will solve this exercise. X equal to y equal to this. Both x and y are the interval 0, 1. And the measure mu, which is on x, is same as the measure nu, which is on y, because both the space are same. Measure mu is same as measure nu, which is equal to measure nu. Both are the big measures. And let's define the function f from x cross y to r, which is the interval 0, 1 cross 0, 1, by f of x comma y is equal to x square minus y square divided by x square plus y square whole square, where this x square plus y square is not equal to 0. That means at least one of them is not equal to 0, and it's equal and the value at 0 when both the points are equal to 0, both x and y are equal to 0, it's equal to 0. And we see that the integral over f with respect to first the x variable, then y variable, its value is pi by 4, and integral of f with respect to first y variable, then with respect to x variable, we will see this is minus pi by 4. We will solve one of them, the second follows on similar lines, just replacing the rule of x and y. Okay, so we evaluate integral 0 to 1, the function is x square minus y square divided by x square plus y square whole square. We'll integrate it first with respect to x, then with respect to y, and we'll see that its value is equal to pi by 4. So let's denote this integral by I. Okay, so this implies this integral I is equal to integral 0 to 1, then integral 0 to 1, this is x square minus y square divided by x square plus y square whole square into dx and dy. Now we try to evaluate first this integral. Now treating in this integral we treat y constant. Integral 0 to 1, let's denote this by I1. Okay, integral 0 to 1 x square minus y square divided by x square plus y square whole square dx. Okay, let's try to evaluate this integral. This is equal to, this is a very simple technique that you have already done in the 12th class. Okay, this y is treated as constant. It's x square plus y square, then minus 2y square, obviously x square plus y square whole square, and minus 2 times integral of y square divided by x square plus y square whole square. Okay, let's denote this integral by, this is equal to say j1 plus j2. Now let's try to evaluate j1 first. Okay, let's try to evaluate j1 first. Now what's this j1? j1 is the integral 0 to 1 x square plus y square divided by x square plus y square whole square dx, and this is just equal to 0 to 1 x1 by x square plus y square. So it's like integral 1 over x square plus, because y square is constant, or you can write it as this dx divided by, it's like a square plus x square. What's the value of the integral? It's 1 over a is here y into tan inverse of x by a is y here. Limit is 0 to 1, and that's equal to, when I apply the limit 1, it's 1 by y tan inverse of 1 by y minus value at 0 is equal to 0. So it's just j1 is equal to this 1 over y tan inverse 1 over y. Now we try to evaluate j2. Now j2, what's j2? It's twice integral y divided by x square plus y square whole square, it's dx. So let me see first this exactly what it's j1 minus j2 here, not j1 plus j2, it's j1 minus j2. Okay, j1 minus j2 is here, not j1 plus j2, j1 minus j2. Okay, so now j2 is equal to integral 0 to 1, it's twice y dy y dx, sorry, y square is here, y square dx divided by x square plus y square whole square. Again here y is constant, so I will write it as integral 0 to 1 y square dx divided by, this is I will write first constant y square plus x square whole square. Then we know that how to evaluate integrals like x1 by x square plus a square, or if there is again square or cube. There is the technique for the evaluating such integrals, a square plus x square or x square plus a square. We are always taking this substitute x equal to a tan theta, because we have a formula for 1 plus tan square, so that's equal to x square. That's why we are using this technique. So here I will put x equal to y tan theta. Okay, the limits will also change. Okay, limits will change, it will change from theta 1 to theta 2. Okay, but you can see here okay, I will not change the limits here. Okay, I will just then this I will not use the limits. Okay, then I have this integral y square dx divided by y square plus x square whole square is equal to, what's y square? Y square as it's, what's your dx? Dx is, it's y times y is constant, d theta is sec square theta tan theta, sec square theta d theta. Okay, this is the integral divided by y square as it's plus x square is y square tan square theta, and then it's the whole square. It's equal to the integral y cube twice. Okay, twice y cube sec square theta d theta divided by this will be y4 times 1 plus tan square theta whole square. This is here this is y4 times 1 plus or tan square theta whole square, that's equal to twice, it's y cube, and y it will be 2 divided by y, because y is treated as constant here. It's sec square theta d theta divided 1 plus tan square theta is sec square theta, then whole square, it's sec 4 theta. Okay. This is equal to over y integral, this is 1 over sec square theta, that's equal to cos square theta d theta. And that cos square theta, it's 2 by y integral cos square theta is cos of 2 theta plus 1 divided by 2. Let me again check this previous page. It's 2 by y cos square theta. Okay, 2 by y cos square theta, and cos square theta is cos of 2 theta plus 1 divided by 2 d theta. This is 2 by y. Now I will integrate it. Okay, integration of cos 2 theta is sine 2 theta divided by, it's 2 to the 4. Okay, plus this is 1 over 2 theta. So this is equal to this 2 will go with this 2 and 2, it's 1 over y times sine 2 theta, that's again 2y sine theta cos theta divided by 2 plus 1 half of theta. Now what is the sine theta and cos theta? As we know that this x is equal to y tan theta, so that means your tan of theta is x by y. So it's the situation is like this. It's treat this as angle theta, this is x and this is y, perpendicular but a base, perpendicular by base, then this will be here x square plus y square by Pythagoras theorem. So then you can easily calculate sine theta. What sine theta? That's perpendicular divided by hypotenuse, it's x divided by under root of x square plus y square. Okay, and this cos theta is equal to y divided by under root of x square plus y square. So therefore we can find the integral. What's this actual integral? So I can again use the limits j2. Therefore the integral j2, which is equal to what was the integral j2 actually? So I have to go the previous page. What's j2 actually? J2 is this integral 2y is integral 0 to 1 y square dx. 2y is integral 0 to 1. So this is j2, which is 2y is integral y over x square plus y square dx. This is your integral j2, and that's equal to it's 0 to 1. Okay. This j2, it's equal to this page again. So here you can see this j2. J2 is actually, so let me say again this j2 is actually equal to, j2 is equal to twice integral 0 to 1 y square dx divided by x square plus y square whole square. This is j2. Okay, let me go to the next page. j2 is equal to twice integral 0 to 1 y square dx divided by x square plus y square whole square, and then its integral is equal to, finally you can see what's the value of the integral here. You can see the previous page, it's integral 1 over y 2y sine theta cos theta plus 1 over 2 half theta, and this 2 and 2 will go, it's 1 over y sine theta cos theta, it's 1 over y times sine, what's sine theta? You can see, you can use the value of sine theta actually. This sine theta is x by root of x square plus y square, cos theta is y by root of x square plus y, so it's equal to xy divided by x square plus y square plus 1 half of theta. Theta is tan inverse, theta is tan inverse x by y. Okay, then I can choose the limits 0 and 1, because I have the variable is now x and y. I have convert the variable theta again into x and y. Now apply this limit here. When I use the limit 1 for because y is treated as constant, the limit is over x, it will be y divided by x square 1 plus y square. So it's equal to 1 by y times it's equal to 1 by y times this is y divided by 1 plus y square, 1 it's y divided by 1 plus y square then this one is 1/2 of tan inverse 1 by y plus 1/2 of tan inverse 1 by y. Okay, then we use the limit, zero limit. Okay, we use the value 0. If x is 0, this part is 0. If x is 0, tan inverse of 0 is 0, so it's equal to 0. It's just equal to that one, this one. So this is your J2. Okay, J2 is this, so which is equal to 1 by 1 plus y square plus this is 1 by 2y. So I have to see this, whether it's 1/2 is there. 1/2 is there. Yeah, 1/2 theta. Okay, it's okay. Oh, sorry, it will be, it's so what's the J1? So this is 1 by 1/2 of 2y into tan inverse of 1 over y. So thus your I1, which is equal to J1 minus J2, that's equal to, what's J1? Let me see the value of J1 here. What's J1? What's the value of J1? I1 is equal to J1 minus J2, and what's this J1? This is J2 here. Where is J1? I have to see that J1 also. J1, I1 is J1 and J2. What's this J1? Value of J1 is 1 over y tan inverse of 1 by y. Okay, value of J1 is 1 over y tan inverse 1 over y. This is 1 over y tan inverse 1 over y. Then minus J2 is this one, it's minus 1 over 1 by y square and minus 1 by 2y tan inverse of 1 over y. I think it's not here 2. There's some problem. I think this cannot be 2 here. Okay, this cannot be 2 here. There is definitely some problem. It's actually here. It was actually here. I think this is not 1/2. Okay, you can see this is actually 2 times this. Okay, you can see it's 2 times this. So this is just theta here. This is just theta here. Actually, this is just theta. Sorry, this is just theta. And then in the next page, okay, go this page. This is just theta here. This is just tan inverse. Okay, this is tan inverse of x over y J2. Value of J2 is plus theta. Theta is tan inverse x over y. So in the next page, then we have